Test. 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 Test, test, test. Come on. Test, test, test. Test, test, test. All right. We got it. It's working. Alrighty, welcome to another stream. Happy Thursday. Almost at the end of the week here. We got a paper that's actually been recommended by one of our Discord community members. I think Freon recommended this one. So thanks, Freon, for the recommendation. I also saw it on some of the other lists that I follow, so I was like, all right, if this is getting recommended by the viewers and it's on a bunch of other lists, then I think we should look at it. So this paper is called, this is the website for it, a little github.io type website. Got Controlling Text-to-Image Diffusion by Orthogonal Finetuning. So text-to-image diffusion is going from text, right, it's a little sentence, into a image, as in a 2D image, right? This is what Stable Diffusion does, Midjourney, all these different generative models in the image space. They're all based around this diffusion architecture. And fine-tuning is the task of taking a more generic model that maybe isn't specialized for a particular visual style or a specific type of person, and then fine-tuning it, aka tuning it finely just a little bit, so that adjusting that behavior so that you get slightly different outputs for the same input. So there's a couple different techniques for fine-tuning that we've actually reviewed all of these on the channel. We have ControlNet, LoRa, which is low rank adaptation, and then this one. This is a new strategy. It's called OFT, Orthogonal Finetuning. So that's what OFT stands for. Yeah, so this is the page. They got a nice little figure. They got some code. Let's actually check out the code. See what that looks like. Ooh, no bueno. 37 stars, that's a very low amount of stars. There's only one file in this code base, and it's just a README with a copy-pasted abstract. So far, the code does not look great. But, you know, sometimes you just catch these things early, and they haven't put the code up, so we don't know yet whether or not they're actually going to release the code, so we'll see. Let's get to the actual paper. So I'm reading this using a PDF extension called PaperPile. I'm not sponsored by these guys, you know. I wish I was, but basically it's a way to organize your PDF library. You can do highlights. You can then search through your highlights. You can do labels and so on. It works in Chrome. It's actually quite clean, but yeah, not sponsored. So we'll see if I maybe switch PDF products. If one of you guys works for a PDF browser plugin kind of company, I'd be glad to try your product. So this work, Controlling Text-to-Image Diffusion by Orthogonal Finetuning, coming out of a couple different organizations here. You have Cambridge, you have Tübingen, you have Mila, which is a group in Canada, in Montreal. You have Bosch Center for Artificial Intelligence, Alan Turing Institute, which I assume is probably also in England. Yeah, so you see this guy is probably British. You see he's both 2 and 6, so he's from Cambridge and the Alan Turing Institute. You have a little bit of weirdness going on here where you have an equal contribution here, this little asterisk, for these two authors, but then they also felt the need to put a little dagger here symbolizing this guy being the project lead. So I don't know why they didn't just put this guy's name in front, and then they didn't need that dagger. But you know, sometimes you can look into the little asterisks and numbers and kind of see a story, you know, because generally this first slot is competed for, and then this last slot is competed for. So these are the two most prestigious positions in the author list. The first one, which means I'm the guy who did all the work, And then the last one, which is I'm the most senior person here. Cool. So let's just dive right into it. Large text-to-image diffusion models have impressive capabilities in generating photorealistic images from text prompts. Sure. I don't even think photorealistic images is necessarily the most impressive thing, right? I think these large diffusion models, they can generate images in an anime style. They can generate comic book style. They can even generate spectrograph images, right? That's something that we were looking at in a bunch of music generation. You can literally generate a spectrogram, which is basically an image that represents a sound. And these diffusion models can do that as well. So I don't even think the photorealism is the most impressive part. I think the ability of these text-to-image diffusion models to kind of generate a huge variety of image modalities is the most impressive part. How to effectively guide or control these powerful models to perform different downstream tasks becomes an important open problem, right? So this kind of age-old task in machine learning of transfer learning, where how can you take something that's been trained or has learned a specific task, and how can you adapt it or transfer it into a new task? To tackle this challenge, we introduce a principled fine-tuning method, orthogonal fine-tuning, for adapting text-image diffusion models to downstream tasks. Unlike existing methods, OFT can provably preserve hyperspherical energy. Okay, so what is a hypersphere? So a hypersphere is a sphere of higher dimensions, right? So you probably have heard of kind of a hypercube, right? These are not. This is a hypercube. Yeah, so here you go. This is actually even better. So this is for cubes, but there's basically the same thing for circles, right? Where you have a line segment, then you have a square. This is 1D, 2D, 3D, 4D. So line segment, square, cube, and then hypercube, sometimes also called a tesseract, right? Which is a 4-dimensional cube. So you could do the same thing with circles. You can basically have a line, which would be a 1D circle, then a circle, which would be the 2D circle. Then you'd have a sphere, which would be the 3D circle, I guess, or 3D sphere. But we don't really have fancy words for a 4D circle or a 5D circle or a 6D circle. We don't. There might be fancy words for that, but one generic term for anything that's kind of beyond 3 dimensions is hyper. So hypersphere is a multidimensional sphere. And one definition for a sphere is that the distance of every point on that is to some center point is the same. So actually, hypersphere. Maybe we can actually get a picture of this. No, we can't. But circles are largely defined by the fact that at every point on a circle, the distance from that point to the center point is always the same, right? So that's very easy to think about in a 2D circle, right? Every single point on the radius or on the circle is the same to the center. It's very easy to think about in a sphere, right? In the 3D sphere, every point on the surface of that 3D sphere is equidistant from the center point, and that property holds for higher and higher dimensional spheres as well. So even though your brain, right, kind of breaks after 4D, 5D, you can't really visualize a 4D hypersphere or a 5D hypersphere, but that property where all of the points on that surface are equidistant from the center is going to stay. Energy has a lot of different meanings. This is like a very loaded term. There's a lot of different terms. Sometimes it means like magnitude. Sometimes there's kind of relationships to kind of entropy. I don't know, but I'm not exactly sure what they mean by energy here. So I think we'll have to keep reading to figure out exactly what they mean by energy in this paper. Characterizes the pairwise neuron relationship. Okay, so neurons, right? Any kind of neural net is made up of individual neurons, and those neurons have connections, right? They have a little they have an edge. You could think of it as a graph, right? Where each node represents one neuron, and then the edge represents the relationship between each of those. And then a unit hypersphere is a hypersphere where the distance to the center is 1, right? So a unit circle has a radius of 1. A unit sphere has a radius of 1. A unit hypersphere also has a radius of 1, except it's a 4D sphere, so it's like even just thinking about that is difficult to do. Hey, Hupo, you are early today. Hey, how's it going? I try to start at 8:30, you know. Sometimes I get angsty and I just start a little bit early, but that's why I kind of try to start a little slow, you know, give people some time to load on. We find this property is crucial for preserving the semantic generation capability, or the semantic generation ability of text-to-image diffusion models. Yeah, so here what they're hinting at is that anytime you're doing this kind of transfer learning or fine-tuning, one of the hardest things that you're going to have to deal with is this kind of catastrophic forgetting, where as you push more gradients for this new task, you tend to forget the original task, right? You overwrite the semantic concepts that were carved into those weights in the initial training. So being able to transfer without effectively fucking with the original model is a hard problem. And if you actually look at the strategies that they compare to here, LoRa and ControlNet, both LoRa and ControlNet, neither of those methods mess with the original model. So LoRa fine-tuning. In LoRa fine-tuning, you're not actually training the original model. Yeah, here's a good picture. What you're doing is you're basically adding this little, so this is a transformer model here. You have tension blocks, you have feed-forward blocks, fully connected blocks, right? You have these residual connections. Here you see that whenever you do a LoRa fine-tuning, you actually freeze the original model. So you're not going to change anything in this original model. You're just going to add this little tiny little parasite and then push weights into this parasite. So you're just training. So one way to think of LoRa and ControlNet fine-tuning is think of it as like if I just took a chunk of brain and I just like put it on top of your head, and then that little brain learned extra information, but your original brain doesn't get touched. So I sometimes use this analogy of like a little parasitic brain that gets attached to the original network. Cool. So to improve fine-tuning stability, we further proposed constrained orthogonal fine-tuning. Okay, so some version of their orthogonal fine-tuning that has some kind of constraint, which imposes an additional radius constraint to the hypersphere. Okay, so that's probably what this unit hypersphere is talking about, where they're probably going to have a constraint that limits this orthogonal fine-tuning to a unit hypersphere, which means that you're going to have a radius of 1. Specifically, we consider two important fine-tuning text-to-image tasks: subject-driven generation, where the goal is to generate subject-specific images. So this is probably put this, I think, let's see. They probably have a good example of this. Yeah, so you have some kind of input images here. They have pictures of this corgi, and then you want to basically fine-tune your generative model such that you can create new images that have this concept of this corgi in them, right? So the corgi is the subject, and you want subject-specific images. They also want controllable generation, where the goal is to enable the model to take in additional control signals. So this is what ControlNet does. This is the other thing they compare to. ControlNet image generation. We also have a video on this if you guys are interested. ControlNet is basically similar to LoRa in that you're basically training this extra little parasitic thing. So much like LoRa. So you see here, you have a neural network, that's been trained on some task that's not the one that you necessarily want. And then you basically add this little extra parasitic brain, right? which you see here, this lock, this is frozen. So you're not touching the original brain. You're just pushing gradients into this little extra parasitic brain here. And the interesting thing with ControlNet is that this little module here is actually receiving a something, right? It's receiving this C. And what is that C? So what that C is things like this edge image, right? Or this pose, right? Or this depth image, right? So basically you can control the output of Stable Diffusion with a additional input, and usually an additional image in the paper. So this is a normal map. This is an edge map. So that's where the word control in ControlNet comes, because you're passing in this little C here, this control signal, which then pushes some information into the original neural network and modifies its output. We empirically show that our OFT framework outperforms existing method in generation quality and convergence speed. So if you've read other papers with us on this channel, this is still very hotly debated. I feel like it's very difficult to measure generation quality, but we'll see what this paper, what kind of metrics and evaluations this paper uses to convince us that the generation quality is good. Introduction. Recent text-image diffusion models achieve impressive performance in text-guided control for high-fidelity image generation. Despite strong results, text guidance can still be ambiguous and insufficient to provide fine-grained and accurate control to the generated images. Yeah, sometimes text is not all you need, right? Sometimes you need, you want to be able to limit it to a specific edge or provide a specific scene composition, right? Or maybe you want to have the specific corgi, like here, right? You want this exact corgi to be in there. So lots of different people have tried to figure out how can you provide better control. To address this shortcoming, we target two types of text-to-image generation tasks in this paper. Subject-driven generation, given just a few images of a subject. The task is to generate images of the same subject in a different context using the guidance of the text prompt. Okay, so given a few images of the corgi, generate that corgi with some interesting background. Given additional control signal, canny edges, segmentation maps. This is the ControlNet, so we actually look at the original ControlNet paper. This is a canny edge, looks like this. Open pose, normal map. So these are pose detect. This is the output of a pose detection model. This is the output of a segmentation model, output of a depth model. Sometimes you can just get this from a depth camera. Canny edge. These are old school edge detection algorithms where you're basically convolving with these little edge filters, and that's how you get these. But being able to control your image generation with some of these 2D signals, control signals. Both tasks essentially boil down to how to effectively fine-tune text-to-image diffusion models without losing the pre-training generative performance. Yeah, you don't want to have this catastrophic forgetting. You don't want to get worse at generating images just because you want to generate an image of a corgi. We summarize the desiderata, a little fancy word there, things that you desire, I guess is what this means, for an effective fine-tuning method as: 1, you want training efficiency. You want to be able to fine-tune quickly. Less training epochs. Epochs is basically whenever you train on your dataset once, right? It's just a way of measuring how many times you've fed the dataset into your model over the learning process. Generalizability preservation. Preserving the high fidelity and diverse generative performance. This is catastrophic forgetting, right? Fine-tuning is typically done either by updating the neuron weights by a small learning rate. So this is the fine-tuning in its most kind of literal sense, and this is whenever you basically push gradients into the original model. And generally what you want is you want to use a small learning rate. If you have a model that you've very carefully trained, Generally, there's a learning rate schedule to that. So what ends up happening is that, right, Stable Diffusion, let's say they trained it for, I don't know, a huge amount of time. The last 25% of the time that Stable Diffusion was trained, the learning rate was so small because of that learning rate scheduling that they spent a lot of time just very slightly changing the weights of that neural net. So if you go in and you try to fine tune it with a big learning rate, you're just basically erasing all that training that happened at the very end, right? All that little extra little moves that you did with that very tiny learning rate. So generally, when you're fine tuning, you want to basically use a small learning rate, and you don't want to train for very long. You just want to train for a little bit. So that's one way of doing it, although this method of fine-tuning is honestly dead. I don't think people are going to be doing fine-tuning in the way that we used to do fine-tuning by basically training on task A and then training on task B. The way that most people do fine-tuning now is this, adding a small component with a reparameterized neuron weights, aka LoRa, aka control net. So this idea of adding this little extra parasitic brain, right? This little LoRa right here and this little control net. So this is really the modern way of doing fine-tuning, is these small components. Despite simplicity, neither fine-tuning strategy is able to guarantee the preservation of pre-training generative performance. There's also a lack of principled understanding towards designing a good fine-tuning strategy and finding suitable hyperparameters such as the number of epochs. I feel like the entire deep learning field is based around a lack of principled understanding. There's a famous talk where this guy called it alchemy instead of science, and I feel like that's still the case. You know, we've made some progress, but I feel like a lot of machine learning is basically experimentally driven, where people just try a bunch of things and they're like, hey, this thing seems to work better, but they can't really tell you why it works better, right? So there's kind of a lack of understanding in terms of why certain things work and why other things don't work. Finding suitable hyperparameters such as the number of training epochs. A key difficulty is the lack of a measure of quantifying the preservation of pre-trained generative ability, measuring how much worse your model is getting at the pre-trained task whenever you fine-tune it on a new task. Existing fine-tuning methods implicitly assume that a smaller Euclidean distance between the fine-tuned model and the pre-trained model indicates better preservation of the pre-trained ability. Okay, so what they're describing here is smaller Euclidean distance just literally means if you take your neural net and then you take the distance of every single weight to every single weight before and after fine-tuning, and hey, if you moved all the weights by a lot, probably not going to have the pre-trained ability anymore. If you only move the weights a little bit, probably going to have the pre-trained ability. But I don't really agree with this, right? I think that Euclidean distance is not going to necessarily be a very good indicator of how much your pre-trained ability has decayed or been preserved, right? Because if you think about it, even with very small learning rates, you can change the behavior of a model. So even with just very slightly adjusting the weights, you can change the behavior. So I don't think that Euclidean distance is necessarily a good way to measure that, but it's a proxy, so people use it. Due to the same reason, fine-tuning methods typically work with a very small learning rate, right? Small learning rate means your gradients that you're pushing are very small, which means that the actual final deltas, right, the changes that you make on the weights are very small, which means that the Euclidean distance between the model after fine-tuning and before fine-tuning is very small. While this assumption may occasionally hold, we argue that the Euclidean difference to the pre-trained model alone is unable to fully capture the degree of semantic preservation, and therefore a more structural measure to characterize the difference between the fine-tuned model and the pre-trained model can greatly benefit the preservation of pre-training performance as well as fine-tuning stability. Okay, so good to hear that the authors kind of agree with me in that Euclidean difference is kind of a bogus way to measure how much you've catastrophically forgotten. Let's come back to this figure. Inspired by empirical observation that hyperspherical similarity encodes semantic information well, we use hyperspherical energy to characterize the pairwise relational structure among neurons. Okay, so maybe this is where they're getting this hyperspherical energy concept from this paper right here, 32. Learning towards minimal hyperspherical energy. Kind of an older paper here, 2018. Okay, so other people have also seemingly used a kind of minimizing the hyperspherical energy as some kind of additional loss or regularization, but it's still not entirely clear what that is. Hyperspherical similarity, probably kind of similar to cosine similarity, I would guess, right? Where you're basically looking at two vectors and then seeing how similar they are. Maybe here just 2 points in a hypersphere. To characterize the pairwise relational structure among neurons, hyperspherical energy is defined as the sum of hyperspherical similarity. So what is hyperspherical similarity? Cosine similarity between all pairwise neurons in the same layer. Capturing the level of neuron uniformity on the unit hypersphere. Okay, so I think what's happening here is that they're basically doing cosine similarity between all the neurons, every single connection of neurons. So one neuron connects to the next neuron, you do the cosine similarity between those, and the more similar they are, the more you have preserved the pre-trainability. So hyperspherical similarity, which is basically a distance metric based around this idea of a unit hypersphere, which is a hypersphere, aka a circle, an n-dimensional circle with a unit radius. They're kind of trying to argue that this similarity metric is better than Euclidean distance. That kind of makes sense, right? I feel like cosine similarity is probably a better metric than just straight Euclidean distance, but we'll see exactly how they're calculating this. A good fine-tuned model should have a minimal difference in hyperspherical energy compared to the pre-trained model. A naive way is to add a regularizer such that hyperspherical energy remains the same during fine-tuning stage. Okay, so here they're kind of setting up what they're going to do is probably they're going to be doing fine-tuning, very similar to LoRa and the control net, where they're probably going to have an additional little thing, right? So they're probably going to freeze the original neural net. They're going to have an extra little thing that they push gradients into, and then they're going to push gradients into it, but they're probably going to have an additional part of their loss, right? An additional regularization term in their loss that minimizes this hyperspherical energy. But there's no guarantee that the hyperspherical energy difference can be well minimized. Therefore, we take advantage of an invariance property of hyperspherical energy. The pairwise hyperspherical similarity is provably preserved if we apply the same orthogonal transformation for all neurons. So when I see the word orthogonal, in my head, in my simple ape brain, I think perpendicular, right? Which is just one line, and then you have the other line, right? Perpendicular, right angles, 90-degree angle. Orthogonal is a more generic definition. You can kind of think of like perpendicular is a more specific version of orthogonal. So orthogonal is kind of like perpendicular in higher dimensions, right? So two things are orthogonal. They basically, the way to think of that in your brain is those two things are perpendicular. So they have some transformation that is orthogonal. And I think this is this whole orthogonal fine-tuning that they're going to talk about here. Motivated by such an invariance, we propose orthogonal fine-tuning, which adapts large text-image diffusion models without changing its hyperspherical energy. The central idea is to learn a layer-shared orthogonal transformation for neurons such that their pairwise angles are preserved. So pairwise angles here, that's just a fancy way of saying cosine similarity, right? When you're doing cosine similarity, you're basically taking two vectors, and obviously these vectors are in a much higher dimensional space, but in your head, just imagine 2D vectors, right? So when you're trying to understand these kind of concepts, I always think it's useful to think of everything in 2D in your brain, just because it's you're not going to be able to visualize 3D, 4D, 5D, right? It's like your human brain is kind of limited in that sense. It's very difficult to visualize higher dimensional things, so you kind of just have to visualize it in your head as 2D. So here we have orthogonal vectors, right? So that perpendicular, and then here you have two vectors, and the cosine between them, right, is this pairwise angle that they're talking about here. So pairwise angle. So vectors that are similar are going to have a very small pairwise angle, right? Versus vectors that are different are going to have a large pairwise angle. Cosine similarity clearly explained. I actually like this channel. You guys should definitely check this out. StatQuest with Josh Starmer. This is a great channel. I don't even know if he still publishes paper, but I do remember this channel. Okay. OFT can also be viewed as adjusting the canonical coordinate system for the neurons in the same layer. Adjusting the canonical coordinate system. So it's some kind of, so the transformation here means that you're transforming, right? You're changing the space. So I guess another way of thinking about that is adjusting the coordinate system. I don't know. I don't have the ability to see how this is the same thing, but let's just keep going here and see whether we can get it. By jointly taking into consideration that a smaller Euclidean distance between the fine-tuned model and the pre-trained model implies better preservation of pre-training performance, we further propose an OFT variant, constrained orthogonal fine-tuning. Okay, so they're going to have a vanilla version of this, and then they're going to have an additional constrained version, which constrains the fine-tuned model within the hypersphere of a fixed radius centered on the pre-trained neurons. Okay, so I think for the normal orthogonal fine-tuning, they're just going to have an additional regularization loss that makes this hyperspherical energy small. But in the constrained orthogonal fine-tuning, the word constraint is more restrictive than a regularizer, right? So regularizer means that you're penalizing for high spherical energy, but constraining the high spherical or to the hypersphere of a fixed radius is more hardcore, right? That means that you're basically like clipping it, preventing it from going beyond the fixed radius of 1, right? And because they keep saying unit hypersphere, I'm pretty sure the fixed radius here is going to be 1, right? Unit just basically means 1. So hypersphere of a fixed radius is basically a unit hypersphere if that fixed radius is 1. The intuition why orthogonal transformation works for fine-tuning neurons partially comes from the 2D Fourier transform, everybody's favorite Fourier series, with which an image can be decomposed as a magnitude and a phase spectrum. Right, so you can take a wave. Let's see if we can get a nice little picture for a Fourier transform. Dude, these are 3 blue, 1 brown. Another great YouTube channel you guys should definitely check out. Okay, none of these pictures are necessarily good. But kind of, if you guys have probably seen this type of stuff before, but any kind of like signal like this, right? So you have some kind of signal coming from some kind of electrical situation. You can break it down into amplitude, right, which is basically the height of these peaks, and then a frequency, which is basically these the frequency, I guess, of like when these peaks occur, right? So it's kind of a way of decomposing signals into these component parts of magnitude and phase. The phase spectrum, which is angular information between input and basis, preserves the major part of semantics. For example, the phase spectrum of an image, along with a random magnitude spectrum, can still reconstruct the image without losing its semantics. So kind of an interesting thing there, but I mean, it kind of makes sense, right? So if you think of an image, right, like, so think about this, right? This is one dimensional, so, but imagine this as an image. If I were to take this signal and just make all of these peaks and valleys deeper, so if I just make that a deeper valley, make that a deeper peak, make this a higher, lower, the original signal is kind of still there, right? It's like the magnitude, you can kind of fuck with you can take this whole signal, multiply everything by 2, and you still kind of basically have the same signal, right? The semantic meaning of this signal is still there, whether or not you multiply the amplitude by a number. So the kind of semantic meaning, the kind of meat of the actual signal is more so in the phase and the frequency, right? So I kind of agree with that. This phenomenon suggests that changing the neuron direction is key to semantically modifying the generated image, which is the goal of both subject-driven and controllable generation. However, changing neuron directions with a large degree of freedom will inevitably destroy the pre-training generative performance. To constrain the degree of freedom, we propose to preserve the angle between any pair of neurons, largely based on the hypothesis that the angles between the neurons are crucial for preserving the knowledge of neural networks. Okay, so they're really kind of leaning in on this analogy of neurons as kind of these vectors, right? So they're basically saying that, let's see, go back to this. You have these vectors, right? They're kind of saying the magnitude of these vectors doesn't matter, right? You make this vector longer, this vector smaller, it doesn't change the cosine of the angle between them, so the similarity is basically the same. So what they want to preserve is the angle between the neurons, right? Largely based on the hypothesis, blah, blah, blah. Okay. It is natural to learn layer-shared orthogonal transformation for neurons in each layer such that the hyperspherical energy stays unchanged. Okay, so this orthogonal transformation that they keep talking about is basically going to transform the neurons, but in such a way that the angle is the same. Okay, so lots of very difficult things to kind of intuit here, to be honest. Like thinking about neurons as angles, but I don't know, maybe we start getting some math here and some equations and some pictures, and then it'll be easier to understand. We also draw inspiration from orthogonal overparameterized training. I've never heard of that before, which trains classification neural networks from scratch by orthogonally transforming a randomly initialized neural network. This is actually, so one paper that I remember reading a long time ago now, which is actually kind of cool, and this is an original Andrew Ng surprising effectiveness. Surprising effectiveness of random CNNs, I think it was called, something like that. Yeah, something like this. So basically, maybe it's not Andrew Ng, but it might not even be this paper. But there was a paper where they basically used randomly initialized convnets in classification tasks, and it actually performed quite well. So that's kind of crazy to think about, right? Where even a convnet where it's just randomly initialized and all the feature maps are basically garbage and all the higher levels of hierarchy there don't actually have anything that's been learned, they still work pretty well for classification. So the universe is still able to extract signal from those basically arbitrary transformations of the data. This is because randomly initialized neural network yields a provably small hyperspherical energy in expectation, and the goal is to keep hyperspherical energy small during training. Small energy leads to better generalization in classification. So, I mean, they're making some pretty bold claims here. Like, I mean, they mentioned this at the beginning here, the lack of principled understanding, but I don't know, they're doing a lot of hand waving with this hyperspherical energy concept. So, is this alchemy, or, you know, are they trying to talk about midi-chlorians here? Like, what's going on? Orthogonal transformation is sufficiently flexible to train generalizable neural networks for classification problems. In contrast, we focus on fine-tuning text-image diffusion models for better controllability and stronger downstream generative performance. We emphasize the difference between OFT and 33, which is, I guess, this work here. Goal of 33. Orthogonal over-parameterized training. This is the same guy, Adrian Weller. Actually, let's go back. I'm pretty sure that's the guy in this paper. Yeah, this guy. Okay. So we're starting to get a picture. There's basically, this seems to be like a whole research direction. Probably this guy here, Weller, who's from, this is the British dude, Allen Institute and University of Cambridge. So this seems to be his particular strain of research here. All right, good to know. So getting a little bit more on the story. Preservative OFT aims to preserve the same hyperspherical energy as the pre-trained model so that the intrinsic pre-trained structure will not be destroyed by fine-tuning. Right, this kind of orthogonal transformation. In the case of fine-tuning diffusion models, minimizing hyperspherical energy could destroy the original semantic structures. Second, OFT seeks to minimize the deviation from the pre-trained model, which leads to the constrained variant. In contrast, imposes no such constraints. The key to fine-tuning is to find a good trade-off between flexibility and stability. I agree with that. And we argue that OFT framework effectively achieves this goal. All right, so now we have the actual contributions of the paper. So at the end of the introduction section, generally you will have a bulleted list of everything you can expect to see in this paper. So of course they're can introduce orthogonal fine-tuning, which is their novel fine-tuning method. Improves stability, limits the angular deviation from the pre-trained model, right? So it's this basically cosine similarity, which they're, or the fancy version of cosine similarity, which is this, in their words here, the sum of hyperspherical similarity, which ends up being hyperspherical energy. So compared to existing fine-tuning methods, OFT performs model fine-tuning while provably preserving the hyperspherical energy, which we empirically find to be an important measure of the generative semantic preservation of the pre-trained model. Okay, so this could be important. Like if this does end up being a useful measure, this kind of hyperspherical energy that they're talking about here, maybe we could see this be used elsewhere, right? So maybe model cards will come with a hyperspherical energy number somewhere. We apply OFT to two tasks, subject-driven generation and controllable generation. We conduct a comprehensive empirical study and demonstrate significant improvement over prior work in terms of generation quality. OFT achieves better sample efficiency as it converges well with a much smaller number of training images and epochs. Okay, so seems like you can fine-tune faster and in with less images, which is good. For controllable generation, we introduce a new control consistency metric to evaluate the controllability. The core idea is to estimate the control signal from the generated image and then compare it with the original control signal. The metric further validates the strong controllability of OFT. Okay, so this is kind of interesting because, you know, they could have just introduced this fine-tuning method and then just kind of ended it there and been like, look at that, it works well. But they're also kind of trying to perhaps provide a little bit of, how do I say this? Explanation? I don't know how to say this, but like tools, right? Like rulers that you could use to measure things. So, for example, they're introducing hyperspherical energy to basically as a measure of generative semantic preservation, and then this new control consistency metric to evaluate the basically how much you're controlling the model when you fine tune it here. So I don't know, these metrics could be kind of the more interesting part of this paper. All right, related work. Text it. Let me get a big sip of this yerba mate before I keep going. Feel free to ask questions, guys, if you have any questions here. You know, we can dive deep on any part of this. Tremendous progress has been made in text-image generation, vision language representation learning, Glide and image gen. Glide changes a text encoder jointly with the diffusion prior using paired text-image data. Image gen uses a frozen pre-trained text encoder. Stable diffusion in DALL-E 2, trained diffusion models in a latent space. Stable diffusion uses VQ-GAN to learn a codebook as its latent space. DALL-E adopts CLIP. CLIP is extremely popular to construct a joint latent embedding space for representing images and text. We really need a better CLIP, by the way, so if any of you guys have the training budget to do so, give us a better CLIP. Other than diffusion models, generative adversarial networks and autoregressive models have also been studied in text-to-image generation. OFT is inherently a model-agnostic fine-tuning approach and can be applied to any text-to-image diffusion model. It's model-agnostic, but it only works with diffusion models, so... Is that really model-agnostic? Subject-driven generation. To prevent subject modification, consider a given mask from users as an additional condition. So, similar to ControlNet, we're going to try to control it with a mask. So none of these are mask. A mask is basically going to be a black and white image where the white stuff is what you want and the black stuff means ignore it. 18 can perform local and global editing without input masks. The methods above are unable to well preserve identity-related details in pivotal tuning. A generator is fine-tuned around an initial inverted latent code with an additional regularization to preserve its identity. Okay, so I've never heard of this, but it seems to be some other kind of fine-tuning technique. 41 learns a personalized generative face prior from a collection of a person's face images. Okay, so other techniques that basically you give it a specific subject and they probably turn that into a vector, and then that vector or embedding is used to condition the generation. 6 can generate different variations of an instance, but it may lose the instance-specific details. With customized token diffuse subject images, Dreambooth fine-tunes text-image diffusion model using a reconstruction loss and a class-specific prior preservation loss. OFT adopts the Dreambooth framework, but instead of performing naive fine-tuning with a small learning rate, OFT fine-tunes the model with orthogonal transformation. Okay, so basically they're just a bunch of different fine-tuning methods that people have come up with. You kind of see some themes with all of these, right? Different regularization terms, additional losses, conditioning on extra things like a face prior. So those are kind of the family of approaches that people have used for these fine-tuning methods. The task of image-to-image translation can be viewed as a form of controllable generation, and previous methods mostly adopt conditional generative adversarial networks. This is GANs, conditional GANs, right? A GAN that is conditioned on an additional thing. Diffusion models are also used for image-to-image translation. More recently, ControlNet proposes to control a pre-trained diffusion model by fine-tuning and adapting it to additional control signals and achieves impressive controllable generation performance. Another concurrent and similar work, T2I Adapter, also fine-tunes a pre-trained diffusion model in order to gain stronger controllability for the generated images. We apply OFT to fine-tune pre-trained diffusion models, yielding consistently better controllability with fewer training data and less fine-tuning parameters. Yeah, you don't want to have a fine-tuning technique that relies on a bunch of extra hand-tuned or hand-picked parameters, right? Making sure that your fine-tuning technique and just your model in general doesn't have all these hyperparameters that you need to tune is very important for using something in practice. OFT does not introduce any computational overhead. So similar to LoRa is like this as well, but the LoRa fine-tuning, right, where you're basically adding this little parasitic LoRa or adapter to the original model, the amount of parameters in this LoRa is way smaller than the stuff here, right? So you're not really, the size of the extra LoRa adapter is very small compared to the size of the original model. So the extra memory is basically negligible, and the extra inference cost is also negligible. So that's important, right? You don't want to have some fine-tuning technique that requires like 10 inference steps and then you average over 10 inference steps. Like, right, you don't want to do anything that is going to make it way more annoying for inference. Fine-tuning large pre-trained models on downstream tasks has been increasingly popular. A form of fine-tuning adaptation methods are heavily studied in NLP. LoRa is the most relevant work to OFT, and it assumes a low rank structure. So the rank, what rank means and what low rank means is that matrices have a rank. So there's a property of a matrix known as the rank, and the rank of a matrix kind of tells you how complicated that matrix is. That's kind of the way I think about it. But let me see if I can find a nice picture. I don't know if I can find a nice picture. But you can think of a low rank matrix as a kind of like a sparse. I don't know if someone's going to yell at me for conflating sparse and low rank, but like that's the way I think about it. It's basically the low rank matrix is the same information kind of repeated over and over again, right? So it's like there's basically I really wish low rank matrix SVD. Yeah, you see this? You see this singular vector, singular value. So low rank matrix has basically a small amount of vectors and values that kind of are representative of all the information in that matrix. Versus a high rank matrix, it's very difficult to basically compress it. So almost, maybe rank is better said is a measure of how much you could compress the information in that. I don't know. Someone's boiling in their seat right now at my shitty explanation of low rank. But low rank adapter, right, LoRa fine-tuning basically abuses the fact that you can create a matrix which has a low rank and thus doesn't mess with the original model that much. In contrast, OFT uses layer shared orthogonal transformation. So additive weight update versus orthogonal transformation. So in a LoRa, you're basically just adding to what's already there. See here? You see this plus? You basically have this pre-trained weight, omega 0, and then you have delta W, which is the LoRa. So it's basically just slightly adding to the existing weights. Versus here, OFT, it's not just going to be you're adding. You're doing this slightly more complicated orthogonal transformation, which is multiplying. And it provably preserves the pairwise angles. Okay, so in a LoRa, you're adding to the existing pre-trained weights, right? And you don't want to add too much. And the Euclidean distance needs to be small, right? So that's kind of, LoRa seems to be keep the Euclidean distance small, because if you have a small Euclidean distance, the original behavior is going to be preserved, and add to it a low rank matrix so that you're not really adding very much. Here in this paper, OFT, they're instead going to be multiplying the neuron weights, and in order to not completely fuck up the weights, when you multiply it, they're going to basically use an orthogonal matrix, which I think is what they show here. Yeah, so you're going to have your original weight matrix. This is the original model. This is going to be your stable diffusion model right here, right? And then you're going to create this extra parasitic brain. But rather than adding that parasitic brain, right, as we do here, right, with the LoRa, you're now going to be multiplying it, right? You see this times. You're going to be multiplying, and this is what you're actually going to be learning or fine-tuning. And the structure of this matrix R, see how it's diagonal here. The structure of this means that the transformation that you're doing to the original pre-trained weight matrix is going to be orthogonal, right? AKA perpendicular. The basic idea is to fine-tune the pre-trained weight matrices with orthogonal transform. More specifically, we transform all the neurons in the same layer with one orthogonal matrix such that the relative angle between any pairwise neurons stays unchanged, right? Because you have this kind of diagonal structure like this, you're not going to be changing the angle between these neurons, which the angle between the sum of the angle between the neurons is what they're defining as hyperspherical energy. Such a property can perfectly preserve the hyperspherical energy. The preservation of hyperspherical energy can prevent model collapse. So what is model collapse? Model collapse, this happens a lot when you're training GANs and generative adversarial networks, but one way to think about model collapse is if you take a neural network, you give it the same input, you give it a bunch of different inputs, and it produces the same output. So basically the distribution of the outputs has collapsed into one value, basically, right? Model collapse. Maybe I can see a little picture here. Let me see. Can I find a good pic? No. I can't find a good pic. But anytime you see the word collapse, just think of like literally that the normal distribution just suddenly going like whoop, and just flattening into almost like a spike in a single place. So it's like collapsed into a single thing. So no matter what you put into the model, it's always going to output the same thing, right? Okay. Orthogonal fine-tuning. So now we're actually going to get into the orthogonal fine-tuning. Let's actually go back to figure 1 because we skipped it. Let's read it and see what's going on. Subject-driven generation. OFT preserves the hyperspherical energy and yields more stable fine-tuning performance across different numbers of iterations. Okay, OFT can preserve hyperspherical energy and perform stable fine-tuning while LoRa and DreamBooth are unable. Okay, so we have our input images of this corgi here. We have 3 different techniques here. They're comparing DreamBooth, LoRa, and OFT. Subject-driven generation is this task where you give in a bunch of images. You basically want to fine-tune the original generative model such that it basically generates corgis with whatever extra text you give it. So you can see here iteration. I think this probably refers to training iteration. And you can see here how as you increase the total training time, DreamBooth kind of begins to degrade, right? So you push gradients, and then you can see how you push gradients relating to these corgis, and then over time, basically, the model starts to lose its pre-trained ability, right? The preservation of the pre-trained ability is lost here. And the same thing happens with LoRa, right? At some point, the little LoRa, the little delta W that you're creating when you have this LoRa, it starts getting big enough that the original model isn't quite doing its job anymore. And I guess here we actually finally get a number for hyperspherical energy. So hyperspherical energy seems like it goes from 0 to 1. And you can see here how the LoRa hyperspherical energy, first it goes down and then it kind of goes up and explodes and gets out of control. But OFT preserves it, I guess. You see how it's stable. It kind of stays at the same value for the entire, no matter how many iterations, right? Obviously that makes sense because they're probably using it as a one of the components of the loss. So it makes sense that it's going to stay stable. And then the DreamBooth goes down. Okay. controllable generation. OFT is more sample efficient in training and converges well with only 5% of the original data set, while both ControlNet and LoRa cannot converge until 50% of the data is present. The hyperspherical energy comparison between LoRa and OFT is fair since they fine-tune the same layers. ControlNet uses a different layer fine-tuning strategy, so its hyperspherical energy is not comparable. Okay, so I guess you can compare the hyperspherical energy of LoRa because the way that LoRa works, you're basically just adding to the original weights. But in ControlNet, you have kind of a separate module here, and you have the original frozen weight. So I guess you can't really use this hyperspherical energy to compare. I don't really know what they mean by this percent of the data. Only 5% of the original data set. I don't know what that means. Maybe it means that you only need 5% of the images to do that. Till 50% of the data is present. So you need less images in order to control it. Uses a different, so, okay, detailed settings. So you have a house. I don't know, all of these kind of look like houses to me. It's kind of hard to... Oh, okay, I see what's going on here. Okay, so you have the house here. You have this picture of a house. And you have this control signal, which is basically a segmentation map, right? You see how you have the different parts of this image, such as house, sky, grass, right? Different categories for each pixel. And then you want this control signal to constrain the generation. So you can see here how OFT, this orthogonal fine-tuning, all three of these generated houses are basically perfectly lining up with this segmentation map, right? So the control signal was able to constrain the generation effectively. Versus here with ControlNet and LoRa, you don't get that, right? You do get it at the end here, so you see how ControlNet, if you have more data, it does manage to constrain the generation, but with a small amount of the original data, it does not. So I guess that's probably why, what they're talking about here. Cool, so now let's actually get into the explanation of orthogonal transformation and orthogonal fine-tuning. We start by discussing the orthogonal transformation is desirable in fine-tuning text-to-image diffusion models. We decompose this question into two smaller ones. Why we want to fine-tune? All right, so they're going to explain to us kind of the reasoning behind this. We draw inspiration from the empirical observation that angular feature difference well characterizes the semantic gap. SphereNet shows that training a neural network with all neurons normalized onto a unit hypersphere. So normalized onto a unit hypersphere basically means that, think about these two vectors here, right? You could normalize them onto a unit circle, right? So you could draw a circle here that has a radius of 1, and then all of the vectors here, you could normalize them such that they basically touch that circle. And that would be normalizing a two-dimensional vector to a unit circle. You could do the same thing in 3D. You could normalize three-dimensional vectors to a unit sphere. And here, what they're talking about is normalizing whatever 500-dimensional vectors onto a 500-dimensional hypersphere, 500-dimensional unit hypersphere. So it's that same thing, just with more dimensions. Yields comparable capacity and even better generalizability. Capacity is basically a word that describes how much a model can learn. So a bigger model generally has more capacity. It's able to learn more abstractions. And then generalizability is a measure of a model's ability to interpolate and extrapolate beyond the original training distribution. So a model that can work for robotics data sets, and anime drawing is very general. A model that only works for autonomous vehicles is not very general. Implying that the direction of neurons can fully capture the most important information from data. Yeah, so these guys are really leaning into this kind of concept that the direction of these neurons, right, the direction of these vectors is where all the semantic information is stored. They just keep doubling down on that time and time again. To better demonstrate the importance of a neuron angles, we conduct a toy experiment where we train a standard convolutional autoencoder on some flower images. So convolutional autoencoder, that's what you have here, right? An autoencoder takes an image or any piece of data, it compresses it into a compressed version of that data. Here they call it a feature map. You could also call it a latent, right? You could also call it an embedding. You could call it a vector, whatever you want to call it. It's just a compressed form of that image. And then there's two parts of it, right? You have your encoder and your decoder. Here it's a convolutional neural net, so they're calling it convolutional and deconvolution. But when you take the image, you feed it through this encoder and then get that embedding and then put that through the decoder, you should get the same exact image back, right? So they train some these two conv nets with some small data set of flowers, I guess. At the training stage, we use the standard inner product to produce the feature map. Z denotes the element output of the convolutional kernel W, and X is the input in the sliding window. So convolutional kernel W, the kernel convolution GIF. How many days in a row have I shown this GIF? I feel like every single time I show this GIF. But the kernel is this kind of like darker thing that's getting convolved, right? So convolution is like a verb, right? You're convolving, and you're convolving the input, which is these blue squares, with the kernel, which is basically this the kind of shadow that's being projected. Z denotes the element output, so in this case, Z is this white thing here. So here it's also a feature map, right? It's two-dimensional. And X is the input. In the testing stage, we compare three ways to generate the feature map: the inner product, the magnitude information, and the angular information. Okay, so they're going to compare three different things here. So here you have A, the inner product. You see here, you're multiplying the weights here by the input, X, and getting Z, the output. Right, so here this T just means transpose, just so that the dimensions work out. And that's the first one here, inner product. The second thing is magnitude. So these double lines just mean the magnitude of this. So magnitude of the weights times the magnitude of the input, and then you dot product that, and that's how you get the Z. And then C, which is the angular information. And now they're basically going to take the cosine of the angle between these things here. So results show that the angular information of neurons can almost perfectly recover the input images. So this is kind of pretty cool. So they show you the inner product, which is what you normally do. You can see here how this encoder and decoder are able to figure out so one cool way to think about autoencoders is that it's two neural nets learning a language that they can communicate to each other in. Right? It's kind of trippy to think of it that way, but I think it's the coolest way to think about it. Where this Z here, this feature map Z, it's a language. It's a language that the convolution and the deconvolution have discovered that allows them to communicate the information in these images of flowers, right? So the deconvolution doesn't get to see the image of the flower. Only the convolution gets to see the image of the flower. And then it converts it into this alien language. And the alien language, which the deconvolution model also speaks, is able to represent the image. So you can see here when the alien language is based on this inner product, you get pretty good reconstructions of the image. When the alien language is just based on the magnitudes, it's basically garbage, right? The encoder and the decoder are unable, they're incapable of finding a alien language that allows them to communicate the information if all they can do is this magnitude. But then, interestingly, if they can communicate with the angular information, they're also able to reconstruct the images, right? So that's kind of cool. I think this is a pretty cool little toy problem here. The angular information can well recover the input, even if the autoencoder is not trained with angles. Yeah, and I think it's important to note it's not quite as good as the inner product, which is what you do in everything, but it's pretty good. Blowing my nose, sipping on this water. We do not apply the cosine activation during training, and the training is done only based on the inner product. It's kind of interesting. So the training is only done on this, but then they tested on that. So it's not like they trained on only the angle. In order to modify the semantic information, fine-tuning the neuron directions will likely be more effective. The second question: the simplest way to fine-tune direction of neurons is to simultaneously rotate and reflect all the neurons in the same layer, which naturally brings in orthogonal transformation. Rotating and reflecting. It may be more flexible to use some other angular transformation that rotates different neurons with different angles, but we find that orthogonal transformation is a sweet spot between flexibility and regularity. Orthogonal transformation is sufficiently powerful for learning neural networks. To support our argument, we perform an experiment to demonstrate the effective regularization induced by the orthogonality constraint. We perform the controllable generation experiment using the setting of ControlNet, and the results are given in Figure 3. We can observe that our standard OFT performs quite stably and retrieves accurate control after training is finished in epoch 20. OFT without the orthogonality constraint fails to generate realistic images and achieves no control effect. Okay, so kind of a weird, like they explain what orthogonal transformations are, and then they just kind of like randomly give you like a little evaluation here where they compare to ControlNet. So you have with the orthogonal constraint, without the orthogonal, and obviously these look like garbage, and then this one looks pretty controlled. So you see how this segmentation map is basically perfectly recreated here. Maybe not perfect, so you see it actually, you have very clearly 4 separate images here, but then if you actually look here, it combined this top painting into 2, or into 1. General framework. The conventional fine-tuning strategy uses gradient descent with a small learning rate to update a model. This is just vanilla fine-tuning. Small learning rate implicitly encourages a small deviation from the pre-trained model, and the standard fine-tuning essentially aims to train the model while implicitly minimizing m minus m0. So the magnitude of m, which is your original, or m0 is the original model, and then m is the pre-trained, or is the fine-tuned version of it. You want to basically have the Euclidean distance between those to be relatively small, right? The distance, these 2 parallel lines mean distance, so the magnitude of this delta m is small. This implicit constraint makes the intuitive sense, but it can still be too flexible for fine-tuning a large model. To address this, LoRa introduces additional low-rank constraints for the weight update. Right, so LoRa is, you're just training this extra low-rank adaptation, right? This delta W, but the delta W is constrained where it can only be a low rank matrix, right? So the rank of this delta W needs to be small, right? I think in the paper they actually say 0, rank 0, rank 1, rank 2, and they like look at the different ranks, and it turns out that you can use a very low rank. Different from LoRa, OFT introduces a constraint for the pairwise neuron similarity. Okay, so this is the whatever HE is, what is HE? Hyperspherical energy. So hyperspherical energy HE. So the hyperspherical energy of M minus the hyperspherical energy of M naught, which is the original model, should be 0. So ideally your hyperspherical energy should not change, right? Which is what we saw. Let me not scroll all the way up there. Let me just do this, which is what we saw here, right? You see this hyperspherical energy, it should be the same. It should not be changing as you fine tune. As an illustrative example, we consider a fully connected layer, W equals W1 to Wn. So these are the weights inside a fully connected neural network. Specifically just one layer of the neural network, right? It's just some set of numbers. Those numbers are real numbers, and the dimensionality of that is d and n, d by n, where d is probably the depth, I guess. They don't define where d is. Where wi in rd, so d, each wi has dimension d, and then the big W has dimension d by n. So basically this is a matrix and these are vectors, right? Is the ith neuron, W0 is the pre-trained weights. The output vector, Z, Rn of this fully connected layer, so you have your output, right? So W times your input X, you get your output Z. Output vector Z, which has dimensionality n, is fully connected layer is computed by Z equals W transpose X, which is the inner product, right? Where X in dimensionality D is the input vector. You see, and this should now make sense why you need this transpose, right? So in order for the matrix multiplication to work out, D by N needs to be N by D, right? So this is D by 1, N by D times D by 1 equals N by 1, which is what the output is. So that's why you need this transpose here, is because the matrix math, you need basically the inner dimensions to be the same. OFT can be interpreted as minimizing the hyperspherical energy difference between the fine-tuned model and the pre-trained model. Okay, so when are we going to actually get a definition of what this hyperspherical energy is? And I think that's literally what they're going to tell you right here. So you're finding the W that minimizes this, right? So this is an objective, and you're trying to find the W that is minimizing this distance here, right? These parallel lines, magnitude of the difference between the hemispherical energy of the original or the new model and the hemispherical energy of the original pre-trained model, right? So this should be as small as possible. You want to find this W that makes this as small as possible. And another way that can be written, and this equation here is just this equation here, but they plugged in what HE is. So HE is a function, and here they're telling you what HE is the sum of each neuron. So Wi is an ith neuron, so neuron I and then neuron J, and you sum over every single pair, right? So this is all pairs, but not to itself. So I cannot equal J. What that means is that you don't do W0 or W, if let's say I equals 1, you wouldn't say W1 minus W1. You can have W1 minus W2, W2 minus W1. So every pair of neurons, but not with itself. And then here, -1 is just the inverse. Where W hat I, so you see this little hat and this little caret, it's called a hat. Wi is Wi divided by the magnitude of Wi, which is basically normalization. Here you're just normalizing it so that it's on a unit hypersphere. W hat I denotes the ith normalized neuron, and the hyperspherical energy of a fully connected layer W is defined as this. W hat I minus W hat J. That actually seems quite simple. Okay, so this whole time they're kind of like building up this boogeyman that is the hyperspherical energy, and you think it's going to be like this absolutely insane, complicated thing, and then it turns out it's literally just this. So that's a relief. One can easily observe that the attainable minimum is 0 for equation 1. Okay, so there, yes, you should basically be able to get a value of 0 for this, but I guess that's really only going to happen if you make no changes. The minimum can be achieved as long as W and W0 differ only up to a rotation or a reflection. So you have W0, you have W, and you have this extra transformation here, R, right? And in order for R to not change the shape of W, the dimension of R needs to be d by d. And it's an orthogonal matrix, right? So orthogonal looks like this. You see this? Most of it is basically zeros, and then you just have the only values are on this diagonal like this. This is exactly the idea of OFT. Wait up. The determinant 1 or -1 means rotation or reflection. This is exactly the idea of OFT, that we only need to fine-tune the neural network by learning layer-shared orthogonal matrices to transform neurons in each layer. So basically, in order to minimize this hyperspherical energy, you're going to come up with these R matrices, and these R matrices are going to be orthogonal matrices. And you're going to learn these. So these are the ones that you're going to effectively learn through this fine-tuning process. OFT seeks to optimize the orthogonal matrix R for a pre-trained, fully connected layer. Changing the forward pass from Z equals W naught Tx to Z equals WTx equals R times W naught Tx. All right, so this is basically... This is the meat of it right here. So normally what you're doing when you go through one feed forward or one layer of your neural net, you're taking your input, you're multiplying it by the weights of the neurons, right? And then you're getting your output. And all they're doing now is they're basically saying, okay, well, let's make the weights of our neural net, instead of just making them W, let's make them some R matrix times W, right? And let's learn a R matrix that will change the output, that will change this Z given the same X for whatever task we want, right? So the Corgi task or whatever, like this subject-driven generation or controllable generation. So it's actually very, very similar to LoRa, to be honest. Except in LoRa, what you're doing is you're learning this thing that you add to the weight matrix, versus here, you're learning this R that you multiply with the weight matrix. So it's basically just LoRa, but instead of adding, you're multiplying. And R transpose times R and R times R transpose is equal to I, which is the identity. So this is basically just telling you that this matrix R should be orthogonal. W denotes the OFT fine-tuned matrix, and I is the identity matrix. OFT is illustrated in figure 4. Similar to the zero initialization in LoRa, we need to ensure OFT to fine-tune the pre-trained model exactly from W0. To achieve this, we initialize the orthogonal matrix R to be an identity matrix. Okay, so at the beginning of the fine-tuning, you need to kind of pick a starting point, right, for this R, and that's what they mean by initialize. Initialize basically means, okay, you create this new variable in your program, right? This variable it's a little tensor which has all the values that you're gonna put for this R, and over time in your fine-tuning, you're gonna push gradients that are gonna change the values of the R matrix. But what are you gonna start it with, right? What are you gonna start with? So what they're going to start with, or what they're going to initialize the R as, is the identity matrix, which kind of makes sense, right? Because identity matrix is just basically a bunch of ones on the diagonal and then a bunch of zeros. So they're going to start this off as just a bunch of zeros and then a bunch of ones. So that the fine-tuned model starts with the pre-trained weights. To guarantee the orthogonality of the matrix R, we can use a different orthogonalization strategies discussed in 26 and 23. Differential orthogonalization strategies. How about that for a metal band name? We will discuss how to guarantee the orthogonality in a computationally efficient way. Okay, so it basically sounds like they're going to have a hard time guaranteeing the orthogonality of this matrix R. Right? And the orthogonality is important because if it's not orthogonal, it's going to change the angle of the neurons, right? And they're kind of this whole, up to this point, they just keep reinforcing this idea that if you change the angles of the neuron, that's kind of where all the informations are. So they really care about orthogonality, so they're going to guarantee the orthogonality. Standard orthogonalizations such as Gram-Schmidt method is expensive. Okay, so you got some weird technique for orthogonalization, which is expensive. Why is differentiable important? Because if you want to basically push gradients, you're going to need to calculate the chain rule. And in order to calculate the chain rule, you're going to have to differentiate different functions. You're going to have to take the partial derivative of functions. And in order to take partial derivatives, you need to make sure that every part of your the thing that you're trying to take the partial derivative of is differentiable. So whatever technique they use to guarantee this orthogonality, it needs to be differentiable. Okay, so this Gram-Schmidt method, apparently it's differentiable, but it's too expensive, so they're not going to use that. And instead, they're going to use Cayley parameterization to generate the orthogonal matrix. Okay, so, I mean, I don't even know what the fuck these are, Gram-Schmidt and Cayley parameterization. Generally, it's not super important, like Gram, how do you even spell this? Gram-Schmidt versus Cayley parameterization. Gram-Schmidt versus Cayley parameterization. Can you explain the difference between Gram-Schmidt and Cayley parameterization? Let's give it a little. You are a fun and engaging math tutor for undergrads in college. Let's give that to GPT-4, and let's also give it to Bard. This is something I do more and more now, is that like I give the same question to both two different models, because models can hallucinate, but two different models, it's extremely unlikely that they both hallucinate in the same exact way. So by looking at kind of these two models, or these two outputs, you can kind of get an idea of what the actual answer is, right? So another way to actually think about what I'm doing right now is I'm literally using a model ensemble. So Gram-Schmidt is used for orthonormalizing a set of vectors in an inner product space, most commonly a Euclidean space of n dimensions. Process takes a linear independent set and generates an orthogonal set that spans the same k-dimensional subspace. Okay, so that's kind of what we want to do, right? We want to basically generate an orthogonal set. Start with the first vector, normalize it, project the second vector, and then normalize. Okay, so it's basically this kind of like iterative, repeat the process. Okay, so you basically, Gram-Schmidt seems to be an iterative process, which actually goes in line with the fact that it's too expensive to compute, right? Because especially if these matrices get big, any kind of process that is iterative like that is going to take fucking forever. Cayley parameterization, mapping between the skew-symmetric, particularly used in robotics. Given a skew-symmetric matrix, find the corresponding rotation matrix using the Cayley transform. Okay, so I don't know what this is. This is basically you take the inverse and then add something to it. So maybe that's why it's better. Typically used, Cayley is typically used in 3D graphics. Okay, so I don't know why the Gram-Schmidt process even exists if you can just literally do this and just do 1i minus a inverse times I plus a. But, okay, let's see what Bard has to say. Two different ways of representing matrices. Vector unit, recursive. There we see the recursive again. More direct way of representing uses a complex number known as the Cayley transform. Represent, blah, blah, blah. Gram-Schmidt is a recursive algorithm where Cayley parameterization is a direct formula. Means that Gram-Schmidt is more computationally expensive than Cayley parameterization, but it can be more flexible since it can be used to represent any unitary matrix, not just those that can be represented by the Cayley transform. Okay, so what I've learned from this, actually, look at this. I like this. I like prose. Flexible, but recursive, so it's slow. And this is direct, but less flexible. So, all right. Now that we kind of know what these things are, let's keep going. Specifically, we construct the orthogonal matrix with R equals I plus Q times I minus Q negative 1, which I think is literally what ChatGPT had. Yeah, that's this right here. Where Q is a skew-symmetric matrix satisfying Q equals negative Q transpose. Such an efficiency comes at a small price. The Cayley parameterization can only produce orthogonal matrix with determinant 1. So this is kind of what we were seeing here, right? Or we were hearing from Bard, where the problem is it can only represent unitary matrices, which I guess is determinant 1 matrix. Unitary matrix has determinant of 1. Yes, okay. So a unitary matrix is a matrix that has a determinant of 1. Which belongs to a special orthogonal group. SO, there's different groups, so if you've ever seen SE2, SE3, SO2, SE3, SO3, these are different groups, Lie groups. So there you go. So two-dimensional rotation matrices are special orthogonal group 2. 3D rotational matrices are special orthogonal group 3. We find that such a limitation does not affect the performance in practice. Even if we use Cayley transform to parameterize the orthogonal matrix, R can still be very parameter inefficient with a large D. So the D here is the size of the neuron, right? Which is basically just how many connections it has. To address this, we propose to represent R with a block diagonal matrix with R blocks. Okay, so here we have the mathematical equation of this picture, right? You see this diagonal matrix with these R1, R2, R3, Rn. This is basically just the same thing, but in math notation. These 3 dots basically just means that they were too lazy to draw in the rest of it, but they show you the 2 corners of what those matrix would look like. OD denotes the orthogonal group in dimension D. All right, so 2D rotations, orthogonal group of 2, 3D rotations, orthogonal group of 3. In this case, we have a n-dimensional, right, or not n-dimensional, but d-dimensional, right, this hypersphere that exists in d-dimensional space that's very difficult for us to visualize and think about. And even more difficult for us to visualize and think about is the orthogonal group in D over R space, right? So even more crazy, right? Try to visualize high-dimensional orthogonal groups. I think that'll explode your brain. Okay, so R is going to be D times D, and R of I is, this is the dimensionality of R here. And Ri, where I guess Ri is the blocks here in the diagonal, R of dimension D by R times D by R. So these have a width and a height, basically, is what they're saying. The width here is D over R. Depending on how many R's you have, right, the side of this is D, right, because it needs to be able to multiply with the pre-trained weight matrix here, right? That's the D. But however many of these you have is the width of that. So D over R is the width of this little tiny matrix here. Or height, sorry. For an orthogonal matrix of size D by D, the number of parameters is D times D minus 1 over 2, resulting in a complexity of D squared. So this is a different notation. So note that. So big O notation for complexity, like you would have in like a LeetCode problem, right? that's the O with this weird little gap there, versus here is the orthogonal group. That's the just normal O. A little bit of confusingness there. For an R-block diagonal orthogonal matrix, the number of parameters is d over r minus 1 over 2, resulting in a complexity of O d squared over r. Okay, so the full matrix, the full orthogonal matrix, this entire brick right here has this complexity, but the complexity of the little R-block diagonal here, just one of these R matrices, is basically over R. So we can optionally share the block matrix to further reduce the number of parameters. Oh shit. Optionally share the block matrix. Damn. Okay, so you're looking at this and you're like, all right, well shit, now we're going to have a bunch of these R matrices. And they're like, no, you're not. They're all going to be the same. Ri is equal to Rj for all I not equal to j. So this little upside down A just means for all I not equal to j. So these are all the same, which is kind of cool. This reduces the parameter complexity to OD squared over R squared. So how is the complexity reduced? Well, it's reduced because you're basically dividing by another R. So the total magnitude of this is smaller. Despite all these strategies to improve parameter efficiency, we note that the resulting matrix R remains orthogonal, so there is no sacrifice in preserving hyperspherical energy. The hyperspherical energy must be preserved. We discuss how OFT compares to LoRa in terms of parameter efficiency. For LoRa with a low rank parameter, we have its number of trainable parameters as R d plus n. If we consider both R and R prime to be dependent on the neuron dimension d, so this neuron dimension, like what the fuck does that even mean, right? And one way to think about that is a fully connected neural net. Is if you actually look at a neural net, right? You look at an individual neuron, such as this little boy right here, this little neuron here, right? It has, look at the arrows that are coming in. It has 1, 2, 3, 4, 5, 6. It has 6 little arrows that are coming into this neuron. Each one of those little arrows that are coming into that neuron has a weight, right? So for every single one of these little arrows that are coming into this neuron, you have a number called a weight. So whenever here, they're like, where is it? Yeah, the ith neuron, Wi, has dimensionality d. What that d is basically just how many of these little arrows are coming into that neuron, right? And if you had a neuron that only had 3 arrows coming in, then everything that we were doing here would be in 3 dimensions, and you could actually visualize this sphere and the unit sphere, and that would be much easier to visualize. But the problem is that this d is not 3. This d is much higher than 3. It's probably hundreds of numbers, right? So that's why it's basically impossible for us to visualize this, because now you can't just say, here, these 3 numbers represent this neuron, and now it's like hundreds of numbers, so it's some kind of like super high dimensional number, or super high dimensional vector in a super high dimensional hypersphere. But if you did this with a little neural net that only had 3 little arrows coming into that individual neuron, or each neuron only had 3 little arrows coming into it, then you would actually be able to visualize all of this, which I feel is actually, they probably should have done that. I feel like that would have been very nice visualizations. The parameter complexity of LoRa becomes O d squared plus dn, and the parameter complexity of O of t becomes O of d. We consider the rank to be dependent on the neuron dimension. Okay, so whenever you're using LoRa, you have to pick a rank. And here they're saying you pick the rank based on this constant alpha. But TLDR, the complexity of LoRa is this. And the complexity of OFT is this. Which is actually huge, right? Because what that tells you, and any of you people who have done like LeetCode or any kind of like programming stuff like that to get into tech jobs, there's a huge difference between a complexity that is O of n squared, which is what this is, versus O of n, right? So what this is telling you is that as the number of connections for each neuron increases, the complexity, the amount of parameters you need for LoRa fine-tuning is going to increase squared, versus for OFT, it's going to be linear. So huge difference in O of n versus O of n squared. We illustrate the difference in complexity with a concrete example. Suppose we have a weight matrix with size 128 by 128. LoRa has 2,048 trainable parameters with a rank of 8, versus OFT has 960 parameters with R squared. Right? So big difference there. Way less parameters. I think it's also important to note that LoRa is not, like, even though here they're saying, hey, you have less parameters, so it's way better, I think LoRa is already pretty small, so I don't feel like LoRa is limited by the number of parameters. So even though OFT is obviously more efficient based on all this stuff that they've shown here, it's provably more efficient in the term of the number of parameters. I don't feel like the number of parameters was holding back LoRa. You know, these are very small little LoRa weights. They're like, compared to the actual size of the model, they're tiny. So even though this is great, I don't know if it necessarily mattered. Constrained orthogonal fine-tuning. We can further limit the flexibility of original OFT by constraining the fine-tuned model to be within a small neighborhood of the pre-trained model. What does small neighborhood mean? Specifically, constrained OFT uses the following forward pass. Okay, so we have a similar kind of thing. You have your output is equal to your input times your weight matrix, and then you are now saying your weight matrix is some new orthogonal matrix R multiplied by the original pre-trained weights, which you're going to keep constant. And here, such that you need to keep this constraint here. The R transpose times R should be the same as R times R transpose equals I, which is the identity matrix. So this is the orthogonality constraint. And then I think here, this is the unit sphere constraint. Orthogonality constraint is this one, right? This one here. And then the sigma deviation constraint, where basically they're saying that R must be very, very similar to this identity matrix. Very, very close. So if we were actually to look at this R matrix, it's probably 1.00001, 0.99998, right? It's just very tiny little values along this diagonal. This orthogonality constraint can be achieved with a Cayley parameterization. However, it is non-trivial to incorporate this sigma deviation constraint into, or epsilon. I think this is epsilon. Epsilon? No. I get this wrong every fucking time. Sigma, Greek letter. No. I think it's just script epsilon. Or, here's the better. This is something I found out recently. You can copy that. So come here. Let's open up the actual paper. Here's a little trick for you guys. Go to the paper. Go down. Get this little here. You copy that. You put it into ChatGPT. What is the name of this symbol? Epsilon. Yeah, but you see the problem is that this is also an epsilon here. Where is it? Here. This one. What about this one? Stop. I got you. Yeah. So there's basically two different types of epsilons. I get confused about this every fucking time. I always see this and then I freak out and I'm like, okay, it's not epsilon because epsilon looks like this, but it's actually, they're just both two types of epsilons. But yeah, that's a little trick. You can actually copy paste characters like that into GPT-4 and it knows what they are. Okay, we apply the Newman series to approximate this. So they're using this weird Cayley technique to ensure orthogonality, right? Which is this weird operation here. And here they're approximating it as I plus 2q plus OQ squared. Newman series converges in the operator norm. Okay, so there's a bunch of these techniques where you approximate things with series, and then these series basically have converged to the actual value that you want. So these are basically infinite series, and then you can calculate the first couple terms, and that's a pretty good estimate to the thing that you actually want. We can move the constraint inside the Cayley, and this is equivalent constraint is q minus 0 less than or equal to epsilon tilde, where 0 denotes an all 0 matrix, and epsilon is another error hyperparameter. Okay, so you have to basically pick the value epsilon here at which you are happy. The new constraint can be easily enforced by projected gradient descent. To achieve identity initialization for the orthogonal matrix, we initialize Q as an all 0 matrix. Constrained orthogonal fine-tuning can be viewed as a combination of two constraints: minimal hyperspherical energy difference and constrained deviation from the pre-trained model. Constrained optimization. The second constraint is usually implicitly employed by existing fine-tuning methods. Despite the excellent performance, we observe that COFT yields even better fine-tuning stability. Okay, so here they show you different values for this epsilon here. All of these are very small. 1e to the negative 7, 1e to the negative 6, 1e to the negative 5. And actually, interestingly, they also use D, the dimensionality of the neuron, as a proxy for this epsilon. So they actually told us here that in the LoRa, they do the same thing. So in LoRa, the rank of the low rank is based on some hyperparameter alpha, which is multiplied by the dimensionality of the neuron. And they're doing a similar thing here as well. This epsilon, which is the constraint, is chosen based on the D. And I guess you can see how as epsilon goes closer to 0, it looks less like this input image. And this is a subject-driven, where is it? Not this. Oh, that is what I wanted. I want this, but I want to go back. Yeah. So in the subject-driven generation, right, you create this new concept of this corgi, and that's what this V means. It basically means you've trained this concept, and you've generally trained it to a specific token, so that whenever the generative model is conditioned on this text here, right, it has this new token V that represents this corgi. So this concept, dog with a mountain in the background. That's basically what's happening here too. This concept, toy on the beach. And you can put whatever concept you want, whatever subject you want in this side, this V token. Intriguing insights and discussions. That's kind of good. They could have just called this discussion section, but they called it intriguing insights section. So I like that. I like it when they spice it up with some weird, fancy, eloquent English. OFT is agnostic to different architectures. Yeah, I mean, based on what they've shown us here, there really isn't any specific weirdness to it. It's like pretty much any kind of weight matrix you could do this with. We can apply OFT to any type of neural network in principle. Transformers is typically applied to the attention weights. Okay, so in transformers, I think they're somewhere over here. We had a picture of it. Here, cosine similarity, control net? No. Whatever. But in the transformer, you have these attention weights. Then you have usually this kind of fully connected layer, then more attention. So it's like the whole block has normal layers and in addition to attention layers. So it seems like in transformers, they only apply the OFT into the attention weights. Yeah. Besides fully connected layers, OFT is also well suited for fine-tuning convolutional layers because the block diagonal structure of R has interesting interpretations in convolutional layers. Okay, so what's the interesting interpretation? When we use the same number of blocks as the number of input channels, each block only transforms a unique neuron channel, similar to learning depth-wise convolution kernels. So when you're doing a, let me bring it up, convolution neural net, right? So this is the depth, right? So you have, wow, what a shit image. You see how there's this depth to it, right? Like as you go further and further higher in this convolutional neural net, you go from 3 channels. You see you have the kernel, which exists in kind of this 2D height and width dimension, and then it has a depth. And then that depth generally increases. So generally as you go higher, right, the actual kind of like X and Y width of the kernel goes down, but the depth, the number of channels increases. So a depth-wise convolution is a convolution in this depth here, right? So what they're saying here is that each block only transforms a unique neuron channel. So the word channel there is basically the depth here, right? So it's the same thing that you have channels in the image, and here you can kind of think of this as the channels in this layer, but it's not the same anymore, right? It's not like actual RGB channels. Now it's basically each of these channels usually represent some kind of semantic concept or some specific texture or something like that. When all the blocks in R are shared, OFT transforms the neuron with an orthogonal matrix shared across the channels. Yeah, and then because we saw that every single R is actually the same R, right? That's something tricky that they threw on us, but apparently every single one of these orthogonal block matrices, block diagonal R's are actually the same R, which is kind of crazy to think about. So it's actually sharing it across all channels. By adding a low-rank matrix, LoRa prevents the information in the pre-trained weight matrix from shifting dramatically. Yeah, basically this whole keep it small and it doesn't change it. OFT controls the transform that applies the pre-trained weight matrix to be orthogonal, but it's full rank, which can also be viewed as preventing the transform to destroy the pre-trained information. Yeah, this is basically their whole shtick, which they're kind of like fusing through this paper, where the information is in the angle between the neurons, not the magnitude. So therefore, if you have a transformation that is orthogonal, even if it's full rank and even if it potentially shifts the weights or the values of those weights, as long as the angles between those are the same, then it should be fine. We can rewrite OFT's forward pass as Z R W naught T X equals W naught plus R minus I W naught. These are just basically they're rearranging this equation up here, right? This equation up here that they gave us twice. They're moving things around, and eventually they get it so that the input is really R minus identity times W naught, which is analogous to the low rank weight update in LoRa. Since W naught is typically full rank, OFT also performs low rank weight update when R minus I is low rank. Similar to LoRa that has low rank parameter R prime, OFT also has a diagonal block parameter to reduce the number of trainable parameters. I mean, they put this nicely, but another way of saying this is that LoRa has an unfortunate hyperparameter R prime. OFT also unfortunately has a hyperparameter R. So for both of these fine-tuning strategies, you have to pick a value for this R. On one hand, we can see from figure 2 that the most effective update to modify the semantics is to change neuron directions, which is exactly what OFT is designed for. On the other hand, OFT can be viewed as fine-tuning neurons on a smooth hypersphere manifold. So it's a manifold is basically just think of a surface. A manifold in a 2D manifold on a 3D space is quite easy to visualize, but in this case, we're talking about a manifold on a n-dimensional hypersphere, so it's very difficult to visualize, which yields as better optimization landscape. So one way that people think about optimization is that you're moving a little marble along a hill, right? And the smoother the hill is, the smoother that landscape is, the easier it is for gradient descent to roll down into a little local minima, right? So smoothness of this manifold is key because it results in better optimization landscape. Why not minimize hyperspherical energy? One of the key differences is that we do not aim to minimize hyperspherical energy. This is quite different from classification problems where neurons without redundancy are desired. The minimum hyperspherical energy means all neurons are uniformly spaced around the hypersphere. Okay, so finally we kind of get an idea here. So the hypospherical energy, the way that they defined it in this paper is the sum of the cosine similarity between each pairwise neuron. So if you have a bunch of vectors, and I'm going to do this again in 2D just because we can't visualize it in higher dimension, but like even though I'm doing this in 2D, they're doing this in higher dimensions. So if you have, let's go back to this one, control net symbol, cosine similarity, yeah. So if you have two vectors and they're constrained to a unit sphere, right? Minimizing the minimum hypersphere energy is going to be vectors that are uniformly distributed around that sphere. So basically, if you had a sphere, you would have a vector here, and a vector here, and a vector here, and a vector here. But they don't necessarily care about that, which is what they're saying here, is that you don't need to minimize that. It's okay if a bunch of those vectors actually point in the same direction. This is not a meaningful objective to fine-tune a pre-trained generative model since it will likely destroy the pre-trained information. Likely, maybe, I don't know. I feel like it's potentially a cool experiment. So I don't know if some of you guys are interested in this as a research direction. I wonder what happens if you minimize hyperspherical energy from the very beginning, right? Like, could you create an additional regularization loss based around minimizing hyperspherical energy and then try to train a stable diffusion model from scratch? Like, is that going to help? Is that not going to help? Right? Did they just kind of discover some new term that everybody's going to put on their loss functions? Maybe, you know. Trade-off between flexibility and regularity in fine-tuning. We discover an underlying trade-off between flexibility and regularity. Standard fine-tuning is the most flexible method, but yields poor stability and easily causes model collapse. Okay. Yeah, I feel like standard fine-tuning is kind of dead anyways because nobody can fit these models onto their GPU. Like, you can't fine-tune these models because in order to even just push a single gradient into these giant models, the optimization state is so big that you basically need to have these big distributed training setups, and nobody has that. So I think just the way that the hardware world exists, I think that these kind of like approaches like OFT and LoRa are going to be by far the most popular approaches for fine-tuning. I think almost no one's going to do standard fine-tuning. OFT finds a good balance between flexibility and regularity. The block diagonal parameterization can also be viewed as a regularization of the orthogonal matrix. Although it limits the fine-tuning flexibility, it brings additional regularity and fine-tuning stability. So they're saying that the fact that they have this block diagonal where every single one of these R's is actually the same, they're saying that that's actually limiting the solution space, right? If each one of these R's could be different, then maybe you could get somewhere more interesting, but by limiting it to using the same R, you're potentially cutting the capacity. COFT is another example of limiting the flexibility. Our method sheds new light. No additional inference overhead. Unlike Dreambooth and ControlNet, our OFT framework introduces no additional inference overhead to the Finetuning model. Right, so in Dreambooth and ControlNet, you're adding this extra module here. So if this module is very big, you have to basically now, your inference is going to increase by whatever the cost of the inference is for this, right? And especially if this C, this thing that you're feeding into the ControlNet, is something like an edge image or a pose image, now you have to add the inference cost of actually running a pose detection model or a canny edge detection, right? So ControlNet is going to significantly increase your inference cost versus OFT and LoRa are no additional inference because all you're doing is just modifying the original weights. In the case of LoRa, you're adding, and in the case of this, you're multiplying. In the inference, we can simply multiply the learned orthogonal matrix into the pre-trained weight matrix and obtain an equivalent weight matrix. Thus, inference speed is the same as the pre-trained model. It's not quite. So, I mean, there is a distinction here. It's not the same because you still have to do this multiply, right? So there's like a loading cost where the very first time that you want to run inference, you're going to have to do this multiplication. But then after that, you're fine because the weight values in your GPU are now correct. But the inference speed is not exactly the same. It's especially if you only have one inference, you're going to have to do one extra multiplication up. But it's pretty much there. Experiment and results, general settings. In all the experiments, we use Stable Diffusion v1.5. So actually, that's kind of the older one. I think they have 2 now. What are they at? 2.1, something like that. As our pre-trained text-to-image diffusion model, all the compared methods fine-tune the same pre-trained model under the same settings. We randomly pick generated images from each method. For subject-driven generation, we generally follow Dreambooth. For controllable generation, we generally follow ControlNet. So here are the different things they're going to be comparing to. They're going to be comparing to Dreambooth, ControlNet, T2I, and LoRa. Okay, so subject-driven generation, this is where you introduce a new concept with some images. So here you have some pictures of this nice little, handsome-looking little cat here, and then the cat is this V. The concept of this exact cat is basically burned into that token, this V. And they're comparing Dreambooth, LoRa, COFT, and OFT. So you can see how as the number of iterations increases here, Dreambooth starts to decay, right? You start to get this catastrophic forgetting. The model gets bad at generating. It starts to forget how to actually generate good quality images. LoRa doesn't have that, but I guess it's not quite as good, right? If you look at here, it's like it's not really getting the concept, and it is starting to lose a little bit of information versus COFT and OFT actually seem to be pretty good. Evaluate the stability and conversion speed. LoRa fails to preserve the subject identity. Dreambooth starts to generate collapsed images. Oh, this is kind of cool. LoRa fails to generate yellow shirt and generates yellow fur. So you see here how the shirt gets lost. Eventually, it just becomes yellow fur. Huh. That's kind of cool. Quantitative comparison. Following 51, we conduct a quantitative comparison to evaluate subject fidelity. Dino and clip I. What's a collapsed image? So collapse is whenever you give the model the same input or different inputs and it gives you the same output. So it's basically it just means that the distribution of outputs is collapsing, right? So like think of this normal distribution collapsing GIF. This. I don't know, I thought there might be a cool GIF, but like basically you could think of it like it just kind of starts generating the same image no matter what you give it. But another way to think about it is just a shittier image. So for example, like here, why would it be generating fur texture here? Well, one way to think about it is that as you keep it, the original model generates images, right? And then you're fine-tuning it with this, right? So you're pushing more and more gradients that say this thing, this thing, this thing, this thing. And in these images, the cat is never wearing a t-shirt. So if you just keep pushing gradients and you keep telling the model it needs to look like this cat, it needs to look like this cat, it needs to look like this cat, by the time you do that 2,000 times, the model's like, okay, well shit, I can't give this cat a yellow t-shirt because it needs to look like this cat, and this cat has fur. So therefore, I'm going to generate yellow fur, right? So like you're collapsing the distribution of all possible images that it can generate into this distribution that is much more constrained, which only includes things that look like this cat. Hopefully that kind of answered your question. If not, I apologize. Okay, so they're comparing here. Here we can just kind of look, but another way that people compare is by using basically these quantitative metrics. Quantitative just basically means numbers. Here you have different models. Whoa, that was a weird like highlight. Did you see that? Like, why did it highlight it as a line? But basically, Dino is a model. It's a big, giant, pre-trained vision model. Clip I, Clip T, LPIPs. These are all basically distances in some kind of model space, right? So you take this Dino model, which is a vision transformer with 16 patches. What is this fucking? Why is it? Oh, it's a strike through. That's why. There we go. And you can say, okay, well, how similar are the real images and the images that are being generated? So here you want high similarity. So that's what this arrow up here means. It means the higher number is better. And you're comparing these different approaches. So I guess this is kind of the pinnacle, 0.8. And then LoRa versus OFT, kind of honestly the same, you know? Which is why I don't like these kind of quantitative metrics, because they don't really tell the story, right? It's like you can look at this table and it seems like OFT is pretty much the same as COFT, which is pretty much the same as LoRa, which is pretty much the same as Dreambooth. But if you look at this, there's very clearly a difference. So I generally like subjective metrics over quantitative metrics. Both COFT and OFT, while achieving slightly better performance, we repeatedly fine-tune with 30 different random seeds. Under the same settings to minimize randomness. So they try a bunch of different random seeds. Random seeds are anytime you have a process, in this case a fine-tuning process, you're going to have to initialize. So there's things that are going to start from random values, right? So they told us that they initialized this orthogonal matrix with an identity matrix and then probably some randomness on top of that, some random normal noise. But the way that your computer generates random numbers, it basically generates them randomly but in a repeatable way. So there's this thing called the seed, right? So if you tell the computer to generate random numbers and you give it a seed and then you give it the same seed, it'll generate the same random numbers again, right? So random seeds are basically a method for guaranteeing repeatably random behavior. But it also means that it's basically an extra hyperparameter because, for example, in reinforcement learning, you can just change the random seed and then sometimes it works. So you try 10 different random seeds and like it works on 3 of them. So only achieves better convergence, but also yields consistently better final results. I agree with that. Qualitative, to have a more intuitive understanding. I like qualitative. Tell me. This is what I want to see. We show some randomly picked examples for subject-driven generation. All the examples are generated. Deliver accident, Dreambooth, preservation. OFT framework achieves better controllability in subject preservation. Okay, so it's basically better. Let's see. Let's see if we come to the same conclusion. So you have input images. This is the subject-driven generation where you're basically giving it these images and then you want to fine-tune so that it creates that. Here's the A this concept dog in a police outfit, A, this concept bull in a blue house with a background. You again have Dream Booth versus Laura versus COFT versus OFT. I mean, these are hard to tell, but I would say that the OFT and COFT are probably better because you can see they keep this same white color and this kind of like ceramic texture, versus the Laura loses it. It makes it blue. It makes it whatever this is, brick colored. Same thing with this clock. This dog. Yeah, I mean, it does seem qualitatively much better. Obviously, like with these kind of things, though, so the negative of quantitative metrics is that they're hard to interpret and sometimes they're misleading. The negative of qualitative things is that people cherry pick. So the negative with these kind of qualitative comparisons is that even though it makes it much easier for you as a human to look at this and determine which one is better, the problem is that these are probably cherry picked. So whoever wrote this paper probably picked the examples that make it look like it's the best. So it could be the case that if you did this with random things, you might have one where the Laura is better, and you might have one where the Dream Booth is better. So you can never fully trust whether or not these are cherry picked, which is the negative of qualitative comparisons like that. Face landmarks. So face landmarks is a type of pose detection for faces. You've definitely seen this, but whenever you're doing face tracking, there's basically these agreed upon set of landmarks. You see these numbers, and there's a couple different formats, but I guess what they're doing here is they're basically saying how much error is there between the landmarks if you have a human here as the subject and you generate these pictures. And I guess it shows you that COFT and OFT have a very low landmark error versus LoRa, ControlNet, and T2I stay relatively high. Okay, so yeah, here you go. Here's the face landmarks. This is Zlatan Ibrahimovic. This is a very famous Swedish soccer player. He has this one crazy Zlatan bicycle kick goal. You guys should definitely check this out. But like this, he basically he does a bicycle kick from like fucking like wherever this is, 30 meters out, and scores it. Absolutely insane. But okay, they're basically trying to generate more images of him, and face landmark is basically a way of determining whether the generated images actually do look like him. It doesn't look like any of these people look like him, to be honest. All of these people just look like random generic looking dudes, but okay. We compute the mean L2 distance between control face landmarks and predicted face landmarks. I just feel like that's not really going to be super meaningful. We plot the landmark error. We can observe COFT and OFT achieve significantly faster convergence. You can fine-tune faster, which is important, right? You want to be able to fine-tune quickly. We focus on comparing OFT and ControlNet because ControlNet achieves the closest landmark error. ControlNet is very hardcore in terms of the way it constrains, right? And ControlNet can also take in not just edge and depth, but it can take in pose, right? So it should be able to take in face landmarks as well. So you should be able to use ControlNet with face landmarks. And you can see here how ControlNet is actually pretty good. So ControlNet is being told to generate a face that is constrained to this exact position. And you can see how it does that pretty well. But COFT and OFT are even better. Like, look at this. These are perfect. I'm looking at the angle of the face, right? That's what I'm looking at, is the angle of the face, not the quality. Same thing here. You see this truck? Look at that. Look how perfect this is. All of them are constrained correctly. See here, this cat is more interesting because this is the tail of the cat in the original image. But here, it starts to hallucinate potentially the arm of the cat. Quantitative comparison. We introduce a consistency metric to evaluate the controllable generation. Basic idea is to compute the control signal from the generated image and compare with the original control signal. We compute IOU and F1 score. Intersection over union. For the S2I, we compute mean IOU, mean and overall accuracy. L2 distance between control landmarks and predicted landmarks. I mean, I feel like just anything that, like any metric like this is basically fucking garbage. Mean accuracy. Yeah, I don't know. I mean, what the fuck does 1.95 versus 0.189 IOU on the C2I task even mean? Right. We can see LoRa completely fails to generate images following the input segmentation map, whereas ControlNet can well control the images. There's no conclusion? That's it? Huh, that's kind of interesting. Usually you have a conclusion section. They just go straight to acknowledgement. I guess they did it differently. They had a kind of a discussion section and then the results. Yeah, so they have a discussion section, then the results, and then no conclusion, which is a little bit unusual. Usually you have results, then discussion, and then conclusion. Kind of cool. I like that, playing with the format of papers. Let's go down to the appendix, where all the super cool little details are. Holy shit, this is a significant appendix. Look at this. This is a 40-page. Failure cases. Oh my god, damn. Look at all this crap here. Different number of diagonal blocks. Okay, yeah, so remember how they said that this, the number of these diagonal blocks, this parameter R, needs to be picked, right? So at some point someone picked what the value for this R hyperparameter is. So here's an ablation study, I guess. Important hyperparameter. And they try R equals 2, 4, 8, and 16. Obviously, the more your R is, the lower the amount of trainable parameters is. Why is there... Yeah, so they shouldn't change the number of inference parameters, right? Because during your fine-tuning, you're training and you're learning the values for these R's, but then once you actually do inference, you're just multiplying your pre-trained weight matrix by this R, and then that's it. So the number of inference parameters is going to be the same. Unfortunately, they only give you these quantitative metrics, so it's kind of difficult to really know, like, how much better is this than this. It's difficult to tell, but it does seem like you can use a lower R and you'll get seemingly better performance. There seems to be some kind of relationship where the performance drops as you increase R, which I guess kind of makes sense, right? If you increase R, what you're doing is you're basically making more of these R matrices, and we know that all these R matrices are the same, so by increasing R, you're basically making this orthogonal matrix the same thing over and over again. It's just the same R over and over again, right? Less parameters. So the bigger your R, the less parameters you have, because all of these diagonal block diagonal R's are basically the same, but it's also going to result in a lower performance. So this all kind of checks out. Proving OFT with magnitude refitting. The fuck is magnitude refitting? My favorite metric, FID. This is like literally the worst metric ever created. Frichet inception distance. It might as well be like what? 30.9 versus 30.8. Like, what am I supposed to interpret from that? I have no idea what that means. Applying OFT to convolutional layers inside of an airplane. paintings on the wall. Yeah, so because you can apply this OFT to any part of the neural net, so it's basically where are you applying it to the attention, just to the convolution, to all of it. That's probably an interesting research direction from this, is figuring out where exactly to add these orthogonal fine-tuning matrices to improve the performance. I'm sure people at Stable Diffusion and other Midjourney, other companies like that, are trying to figure that out themselves. COFT versus OFT. COFT is the constrained OFT, which is basically just one additional constraint that constrains it to the unit hypersphere. I don't know, kind of feels like it's the same. It's hard to tell. More qualitative results. Let's look at the failures. They said they had failures all the way at the bottom. So the anti-cherry pick is failure cases. So I guess this is a failure because it's not that. So here you have a failure case where it has a really hard time coming up with stairs that like fit this like weird amphitheater type pattern, and it tries to create this kind of weird tangle of ladders or stairs. A red cat. This is actually very impressive because I don't think there's a single example of a red cat in the Stable Diffusion training data set. A cube-shaped dog. Pretty cool. All right. Where are we at? A little bit over 2 hours. Okay, let's do a summary of this paper and then we'll end it. Okay, so today we looked at controlling text-to-image diffusion by orthogonal fine-tuning. This was a paper very similar to LoRa fine-tuning and ControlNet fine-tuning, where basically the idea is to fine-tune a existing text-to-image generative model. So fine-tuning a text-to-image generative model is generally done for the purposes of adding additional capabilities and specifically things like subject-driven generation, where you want to say, hey, I want to generate a dog with a mountain in the background, but I want this specific dog, right? So what you're doing when you're fine-tuning is you're pushing gradients related to the concept of this specific dog. So vanilla fine-tuning is actually just loading the entire model and then just pushing gradients directly into that model, and nobody really does vanilla fine-tuning because it's very computationally expensive, and it's actually not very great because you have this kind of catastrophic forgetting problem. Techniques that are popular now are LoRa, and what you're doing in LoRa, which is low-rank adaptation, is you're basically freezing your original model and learning this low-rank adapter, which is basically just like a little some delta W. You see this delta W here? That you can then add to your original model, and then it'll change the behavior slightly, right? ControlNet is a similar kind of idea, but you actually have a separate little parasitic brain or neural net module here that takes in some kind of condition here, some kind of control C, where that control is a maybe an edge map or a segmentation map or something like that. So kind of similar to both of those ideas, what this paper does is it introduces the idea of this orthogonal matrix. So you now you keep your original pre-trained model frozen, and you basically have this new matrix R, which is constrained to be orthogonal, right? And the reason that it's constrained to be orthogonal is because it wants to keep the hyperspherical energy the same. And hyperspherical energy sounds like some kind of healing crystal thing, but it's not. What a hyperspherical energy means is basically the and where is it? This exact definition. where do they define it? Yeah. The hyperspherical energy is the sum of hyperspherical similarity, which is basically just cosine similarity between all pairwise neurons, right? So basically, think of it this way, where basically you want this R matrix to change the values of these vectors without changing the angles between them, or just very slightly change the angles between them, right? So it's kind of like the same energy as LoRa, but just a slightly different thing. Rather than adding extra weights, you're basically multiplying by this R matrix. And it has, they make some interesting kind of reasoning here, where they basically show that this the angle between these neurons is actually more important than the magnitude. They make some analogies here, little toy examples. Here are the actual constraints that they use. So normally OFT, so there's two different versions that they introduce in this paper. OFT just has this orthogonality constraint here, but they also have a more constrained version, which they call COFT, and COFT has this additional constraint here. So it has the orthogonality constraint, but then it also has this R minus I less than or equal to epsilon here, which they call the epsilon deviation constraint, but basically it constrains to a unit hypersphere. So yeah, and then they go and they show you, and it does seem to actually perform quite well. It doesn't seem to impact the pre-trained behavior of the original model. It seems to kind of not fuck with the original model too much, and it does seem to effectively adapt it in such a way that a new concept can be learned here, such as this cat wearing a yellow shirt. And comparing it to LoRa and Dreambooth and a couple other fine-tuning approaches, it does seem qualitatively better, at least in all the examples that they provided, but we also don't know whether or not they're cherry-picking super hardcore, so it could be the case that they're lying to you and it's really not that much better. But it does seem to train faster, and it does seem to use less parameters, and one important thing that they did mention here is that up here, yeah, the number of parameters, depending on the dimensionality of the neurons, has a different complexity than LoRa. So LoRa has this kind of n squared complexity versus OFT has this O of n complexity. So that's actually pretty promising there as well. And yeah, that's pretty much it. Pretty cool little paper. Honestly, excited to see what people do with this. It seems like this could be pretty big. The actual code is kind of nonsense, unfortunately, right now. It's literally just a README, but hopefully we get something here. But honestly, it's not a very complicated concept. It's actually very simple, right? So I don't think we're gonna have to necessarily wait for this code to get released. I think people will probably be re-implementing this pretty quickly, and we'll have a bunch of different re-implementations of this. But yeah, that's it. Pretty surprising how kind of simple their method was. Yeah, I think it's refreshingly simple, right? I was kind of concerned. I kind of read the abstract and I was like, holy shit, dude, what the fuck is a hyperspherical energy? And then it's actually quite simple. It's basically just this. You're just minimizing cosine similarity, or not cosine similarity, the hyperspherical energy, but pretty badass. I like it. Thanks for listening, guys. Hopefully that was useful. This was kind of a dense one. Tomorrow we have a paper that is actually quite simple and easy. It's more of a framework paper, so it's about robotic simulations. So if you guys are interested in that, definitely tune in. If not, you guys have a great weekend, and see you guys later.